we're gonna take fundamental theorem of calculus version 2. I'm gonna try to break it down with these first two examples in a way that makes sense to us based on what we already know about the fundamental theorem of calculus, i.e. version 1. And then ultimately we're gonna kind of come to a shortcut for when we see problems like this. So again, skipping the top part on the area, I'm gonna try to make sense of this in a little bit of a different way. So we have lots of notation in these first two examples, and I'm going to try to break it down for you. Big picture, we're taking the derivative of a definite integral of a function. Derivative, definite integral function. Okay? I want to go back to our understanding of what a definite integral is first. So I'm going to take this portion, and I'm just going to ask the question, what does that mean? Okay, area, net area or total area? Net area under a curve. I'm not 100% sure what this curve looks like. I'm just going to draw a sketch. You don't need this sketch. But I'm going to start at 1, and I'm going to go to what? I'm going to go to some unknown upper limit, a variable upper limit. Call it x. And I don't really, this is a cubic function, so I mean, who knows? It could do something like that. I don't know where that ends. But the question is, this portion, not the question is, but this portion represents an area. Okay? It represents an unspecified area. Now, it's not an infinite amount of area. It's a bounded area, but it's bounded by a variable. So what this allows us to do is, it's kind of like that problem number 11 from the homework that we just went over. It allows the upper limit to change. If we go back to that example 11 from the homework. Okay? Then, once I've found that area, or an expression for that area, what are we going to do? Take the derivative of it. So we're going to find an area, and then we're going to take the derivative of it. So we're going to find an integral and a derivative. We're going to find an antiderivative and a derivative. What should happen if you take an antiderivative and a derivative? What should happen? You should get the function. Shall we go through this to see? Because it's not, you're going to get the function, but it's not always that simple. So I'm going to do this the long way, guys, and we're going to draw some conclusions. And then whenever you see a problem that has an integral and a derivative and a variable upper limit, you're going to be able to use fundamental theorem of calculus version 2. But I'm going to we're going to walk through this first to demonstrate, using a process we're familiar with, that you're going to get the function back. You ready? Will you write this down? Okay. I'm going to deal with the integral first. And in evaluating a definite integral, we're going to use fundamental theorem of calculus version 1, which means I will take an antiderivative of what's inside here. Antiderivative of t cubed is t to the 4th over 4. Antiderivative of 2t squared is 2t cubed over 3. Antiderivative of 4 is 4t. I'm then going to evaluate that from 1 to x. Even though I've got a variable there, I'm going to go ahead and use fundamental theorem of calculus version 1 for that antiderivative. That's FTC 1. Okay? And once I feel like I've evaluated this integral sufficiently, I'm going to take a derivative. Keep that in mind as we move forward. Okay? Yesterday we learned that I put in the upper limit first, I put in the lower limit second, so this is going to be x to the 4th over 4. Actually, this is how I showed it, didn't I? Parentheses minus parentheses, the function evaluated at the upper minus the function evaluated at the lower. So this will be x to the 4th over 4. I'm putting x in place of t because it tells me to there. Plus 2x cubed over 3 plus 4x. That is capital F of x, the function of, or the antiderivative evaluated at the upper limit. Okay. What do I put in the next set of parentheses? I let t be 1, right? And t being 1 is pretty easy, isn't it? 1/4 plus 2/3 plus 4. Okay. Good so far? Will somebody evaluate that for me? Somebody evaluate this portion, would you? And calculator's fine. Give me a fraction for that if you would. Its common denominator would be 12, so this would be 3 over 12. This would be 8 over 12. And this would be 48 over 12. So 59 over 12. X to the fourth over 4 plus 2x cubed over 3 plus 4x minus 59 over 12. What have we done so far? What does what I've written here in blue represent now? What can I do with it? If I knew that x was 8, what could I do with this? What would I be finding? If I knew that x was 8 and I let this put it in here, what would that give me? It would give me the value of the integral from 1 to 8, right? The net area between 1 and 8 under this curve. Okay? So now I've sufficiently evaluated that. That's hard to put into context, but it represents an area function where the right-handed limit of the region is allowed to change as x changes. Okay? What am I going to do with this now? I took care of the stuff inside the box. What am I going to do? I am going to find the derivative of this. And many of you are already half a step ahead of me. What's the derivative of that mess? What's the derivative of x to the fourth over 4? X cubed. What's next? 2x, right? 2x, we take the coefficient, we multiply by the exponent by the coefficient, plus 4, 2x squared, thank you. 2x squared plus 4, what happens to 59 over 12? Derivative of that is 0. How in the world do we explain this relative to this? Or is it that simple? Does it make sense? If I'm doing a derivative of an antiderivative, shouldn't I get the function back? Okay. What I'd like you to do is don't take my word for this. I would like you to use a similar process on number 2. I'll give you about 3 minutes. The thing to notice is that the inside the function, the f of x, is the same. This is different, though. When you get to this step in the process, it's going to look a little bit different. But will you, number 1, use the fundamental theorem of calculus version 1, and number 2, take a derivative to see if you can come up with a pattern or a rational explanation for what is supposed to happen when the upper limit is not just a variable, but an entire function. I'm going to give you about 3 minutes to play with that. I had the mic off for that entire portion. So whoever's watching the video is going to have to just watch. Great explanations, just got lost in the audio. Okay, so hopefully we're okay at that point. What you should consider being able to do moving forward, when you have lots of terms, you want to look for what's common and you want to factor it out. What's in all of them? All of them have a 3x squared. So I'll take a 3x squared out front. That leaves us with x cubed plus 1 cubed plus 2x cubed plus 1 squared plus 4. What's the pattern? How is the answer we got here related to this and this and this? Anything jumping out at you? I want a shortcut now because I don't want you to have to go through that every time. What do you see? Take the derivative of the upper limit, the variable upper function, yeah, and put it in front. And you substitute the upper limit into the original function. Okay, do you see that a little bit? Can you apply that to, gotta clear my notes from last hour. Can you apply that to this? Go to the next page of your notes. Here's what I want you to be able to do, and here's what the AP exam is going to ask you to do, because you can't. If I go back to this one, we can do this process by doing an antiderivative and then taking the derivative again, right? The long way. But when you get to a function like this, anybody know the antiderivative of e to the t cos t? Not today. There's no way to find this antiderivative to take this process the long way. So we need to take the pattern that we learned, which is called the Fundamental Theorem of Calculus version 2, which I'm going to write formally in a minute, to evaluate this. What's this going to look like? What's the answer to 3? E to the x cosine of x. That's a lot easier than the process we just went through, isn't it? But you wouldn't believe it. You wouldn't believe it if we hadn't gone through it. Okay? What about number 4? Will you write your answer to number 4 and show it to a neighbor? What you should have for the second one, check to make sure you got something like this. I'm going to do this kind of the long way. You could have gotten this way. I'm not going to do it the long like we did it before. But this would be x cubed squared. This would be x cubed. And then I need to multiply by 3x squared. What's 3x squared represent? The derivative. This is, if this function up here is g of x, this piece right here is g prime of x. That chain rule keeps coming back to us, doesn't it? It kind of applies there. Okay? You can simplify if you want. You don't need to do a whole lot here. I might write my answer, or AP might write their answer as this. They probably wouldn't circle it though. Okay? Good so far? All right, so we want you to do this in general. If the upper limit is a single variable, call it x. This is a variable upper limit. The derivative with respect to x of the integral from a to x of f of t dt is f of x. Good. F of x. It's not f of t because I got to put in that variable upper limit. Is f of x. Okay. If the upper limit is a function, what's the value of the derivative of the antiderivative? I'm going to write it like this because it reminds me of chain rule. And this is kind of how I write chain rule. But whatever order you do it in is okay. Just make sure you multiply by the composition of the functions and the derivative. Okay? Will you add your own meaning here in words? I think it should have something to do with the function evaluated at the upper limit times the derivative of the upper limit. And the derivative of the upper limit, believe it or not, the derivative of the upper limit piece applies there too, because the derivative of x is 1. So you can always use chain rule there. Okay? I want you to try example 5, and then we will do 6 together. If you're feeling adventurous, you can start on 6, but be careful. All right, with 5, you got sine of cosine of x times negative sine x, right? Did you get that for number 5? How many people got that? High five yourself, everybody. Got it or not? High five yourself. Good work. Okay. All right, now, there's a couple of ways I'm trying to wrap my mind around number 6. Okay? Will you first turn your packet to the last page of notes and go to property number 4? Actually, I want you to look at 2 properties. I want you to look at property number 4, and I want you to look at property number 9. Nope, that's not what I wanted. Pause. 10. Look at 4 and look at 10. Okay? And because I'm going to use both of these. I'm going to use 4 and I'm going to use 10. If I look at property 4, we haven't talked about this. You may have experienced it a little bit on Friday last week, but if I take the bounds of integration, we're used to going from A to B, right? What if I went from B, I made a B backwards. What if I went from B back to A? What if that whole region, rather than integrating from left to right, what if I integrated from right to left? Would that be weird to you? The common method is to go from left to right, and we use delta x's. What would happen if I went the other way? Would it make sense that that entire area would be the opposite? Because a Riemann sum adds up left to right. If I go from right to left, it's the opposite. So number 4, we're going to use in just a minute. The way I think of it is I think of the dx value as negative. You know how when we went below, we considered the function value to be negative? If I go backwards, I consider the dx value, the delta x value, to be backwards. Okay? And then look at number 10. Make sense of it. If I want to integrate from A to C, I could break it up into 2 integrals, couldn't I? If I'm starting at A and going to C, I could break it up at some value B and I'd get the same value for the integral, right? We actually did that yesterday with the area under and the area above, didn't we? Okay, so here's how I'm going to wrap my mind around this, and then you can help me wrap my mind around it in a more complex way. So with this, what's new here is that we don't just have a variable upper limit, we have a variable upper and lower. And up to this point, we've just done a variable upper limit. Okay? Even though it's a little bit mind-blowing that the lower limit doesn't mean anything, we'll move past that for now. You don't need the lower limit in order to find the value here because you're just evaluating at the upper limit. I'm going to take this one and I'm going to break it up into 2 integrals. Okay? I'm going to actually break it up into 2 derivatives and integrals. So will you write this for me? I'm going to go from sine x to some value a of u squared du. And I'm then going to go and differentiate and integrate from a to cos x of u squared du. As long as a is in between sine x and cosine x, that's good, right? So I'm just adding some constant in the middle to break up those 2 integrals. Okay? Which one of these 2, red or blue, did we learn how to do today? The red one or the blue one? The blue one. We learned how to do the blue one today. And this should be pretty simple at this point. I've got a constant lower limit and a variable, i.e. function upper limit. So this should just be cosine squared x times negative sine x, right? That's what we learned today. That's fundamental theorem of calculus version 2. F FTC version 2. Okay? The red one's not quite ready. It'd be really nice if the red one had the other boundaries, though, wouldn't it? So based on that property 4, I'm going to do this. I'm going to take the integral, and I am going to flip the bound. So I'm going to go from a to sine x rather than sine x to a. I'm upside downing the lower bound and the upper bound. This is still going to be u squared du, and I'm going to maintain the d dx. But when I switch the integral, the interval of integration, when I switch the sine to a, and I switch it to a to sine, what do I have to do to the integral? Make it -1 in the front of it, right? Now, do we know how to do the red one based on fundamental theorem version 2? We do. What is it? It's sine squared x times cosine x, and there's a negative in front of it. And then I throw the blue one in there, and I end up with cos squared x sine x, and that is the value. Now, my 5th hour class did it faster than that, and you tell me whether or not this makes sense. I'm trying to wrap my mind around whether or not this is accurate, and I think it is. What someone 5th hour did was they went ahead and just evaluated at the upper bound and evaluated at the lower bound and subtracted. That's like FTC version 2 with FTC version 1 in the same problem, isn't it? So if I let u be cos x, I would have cos squared x, but then I apply the chain rule piece, negative sine x. That's capital F evaluated at cos x, isn't it? Kind of a fundamental theorem 1, fundamental theorem version 2 hybrid, if you will. And then subtracted capital F of sine x, which would be sine squared x times cos x. We end up with the same thing, don't we? I'm still trying to wrap my head around that, but I think it's cool to think about, and I think it's worth trying. Okay? On the last page of your notes is just a big old list of those properties. Okay? We highlighted 4 today. We highlighted 10 today. These 11 and 12 we haven't really dug into yet, but I want you to think about even functions and odd functions and think about those graphically and see if you can make sense of those integral properties. Your homework is day 2. We're going to have tomorrow, this is just for my classes, we're going to have tomorrow as a day to do corrections and a day to kind of dig in on the fundamental theorem homework.